today we are going to read the book, A Drop of Water. And it's a book of science and wonder by Walter Wick. And today I thought that we would read it where I'm showing you the pictures and you can see me reading it the whole time, because this is one of those books that the images really add to all of the features. So I really want you to be able to see those. So I'm going to do a quick wave so you can see me real quick. Hi. Hello. But so I am reading that, and yeah, you can see the light there. So hopefully you'll be able to see these pictures very well. All right, so we're going to read A Drop of Water, book of science and wonder. And I thought of this, especially with all of the snowfall and us going into colder weather. It's really interesting to see all the different parts of water that we don't really think of. So this is for Linda. We are going to spend an hour today in following a drop of water on its travels. If I dip my finger in this basin of water and lift it up again, I bring with it a small glistening drop out of the water below and hold it before you. Tell me, have you any idea where this drop has been? What changes it has undergone, and what work it has been doing during all the long ages water has lain on the face of the earth? Arabella B. Buckley in 1878 said that. So I think that this little introduction is kind of going to tell us a little bit more about water. So, water's smallest parts. A drop of water falls through the air. Down it splashes, breaking apart into tiny droplets. What would you see if you could break water into even smaller bits? No matter how closely you look, you can't see water's tiniest parts. Like every other substance in the world, water is made of very tiny particles called molecules. On the pin above, see that? The smallest droplet contains more than 300 trillion water molecules. By the way, here's an actual pin size. You can see how blown up it is over here. So you can see that difference. Water's elastic surface. Step by step, a camera reveals the curious changing shape of a drop of water as it falls from a spout. The drop grows heavy and begins to fall. As it breaks from a strand of water, the drop shrinks itself into a round ball or sphere. The drop flattens, then elongates as it falls. The strand, meanwhile, breaks into tiny droplets. The impact of the drops hitting the water causes a new strand to bounce back out as another drop breaks away. See how they're explaining it? It's going down, it gets along, and there's that sphere, drops down. And then once it hits, look at it goes down and a whole bunch go up. See it? Because water molecules cling to each other like tiny magnets, a drop of water can stay in one piece even as it falls through the air. But the molecules at the water surface cling with a force that causes the surface to shrink. This force is called surface tension. When the surface of a drop of water shrinks to its smallest size, the drop forms a sphere. The sphere stretches because of the drop's weight and motion, but surface tension helps keep the drops together as if it were held in an elastic skin. So this is floating steel and wild waves. This steel pin seems to float magically on the water. In fact, the pin is not really floating. It is held by the water's surface tension. This works only if the pin is very carefully lowered onto the water's surface. Otherwise, the pin will sink. An egg dropped from above, see this one? And then that was the pin, sorry. An egg dropped from above transforms the calm surface of water into a wild wave. Immediately, surface tension forms wrinkles in the water, breaks the jets of water, and shapes the smallest droplets into tiny spheres. See those spheres there? See all the little balls? The spheres, they're round. Sometimes it's really interesting. I mean, I know we drink water, we see water, we bathe in water. Water is all around us, and we've been talking about this abiotic factor in science. However, Sometimes when you look at it and really think about it, there's so much more to it that we don't always think about. We really take it for granted. Look at that. When water meets air. A dry paintbrush is fluffy. The bristles of a wet paintbrush cling together. But the bristles of the paintbrush in this jar are wet and fluffy. Why do the two wet brushes behave in different ways? The brush in the jar is held below the water's surface. Water surrounds the bristles, but has little effect on their positions. The wet brush outside the jar is surrounded by air. Water molecules don't cling to air, so they pull together and bring the bristles together too. Of the two wet brushes, only the one outside the jar is affected by surface tension. Wow, so I mean that is such a simple thing that you've been doing since you were a little kid, and probably didn't think about how a brush is, how it acts when it's dry, when it's wet in the air, or when it's wet in a jar, and how they are very alike and different. So there are some scientific reasons why things act the way they do. So just a really cool connection to some of those scientific ways of thinking and just kind of seeing what we can test out here. So when the water flows up, gravity causes water to flow downward, yet water has actually flowed up into these glass tubes. What could cause such strange behavior? Water molecules cling to materials such as glass with an attractive force called adhesion. That's why water drops clings. Let me try that again. That's why water drops cling to window panes after a rain. This attraction is also what causes water to creep up the sides of the glass tubes. The narrower the tube, the higher water will climb. This behavior is called capillary attraction. Anywhere water creeps through crevices, tiny spaces between grains of sand or fine veins in the stem of a plant, capillary attraction is at work. Wow, so we're talking about some science concepts that we don't study in 5th grade science, like surface tension, adhesion, or capillary attraction. But, just a simple water description is what explains all of those things. So, you are going to think about those things later on, but maybe just thinking about and seeing how water can be presented and look in different ways, maybe it will get your mind thinking too about some of these other connections. Ooh, soap bubbles. Those are super fun. There are few objects you can make that have both the dazzling beauty and delicate precision of a soap bubble. Shown here at actual size, this bubble is a nearly perfect sphere. Its shimmering liquid is 500 times thinner than a human hair. Wow, that's really thin. So think about how thin your hair is. It's 500 times thinner than that. So you know that those are very, very delicate. Bubbles made of plain water break almost as quickly as they form. That's because surface tension is so strong the bubbles collapse. Adding soap to water weakens water's surface tension. This allows a film of soapy water to stretch and stretch without breaking. When you blow a bubble, it looks somewhat like a drop of water emerging from a faucet. And just like that, the surface of a drop of water, the bubble's surface shrinks to form a sphere. Spheres and circles are mathematical shapes. Because they can form spontaneously, they are also shapes of nature. The circle below formed instantly when the film inside the loop of string was broken. So look, somebody dipped that in, there's like string there. And when they pulled the string and made a circle, look, it made a hole there. So we have that air that, that film inside that string was broken. So now it's like air right through there. Those are soap bubbles. Ooh, look at the bubble shapes. So if you dip any wire frame into soap solution and pull it out, the wire edges will be connected with bubble film. The film shrinks, revealing the smallest possible surface area within the structure. And when this frame was pulled out of the soapy solution, 12 panes of bubble film connected at the center of the frame. A straw was used to blow a bubble in the center. The 12 panels pulled that inner bubble into the shape of a cube. See how it's like a cube? That's really cool. I know in the wintertime, sometimes people do little science experiments with soapy water, do bubbles and try to make them freeze outside. I wonder if that's something that you could do. That's really cool. Ooh, look at the molecules in motion. If a drop of water is added to a jar of still water, and if the water in the jar is not stirred, where will the new drop go? It will stay near the top. Will it stay near the top or sink to the bottom? A simple experiment reveals the answer. A drop of blue water enters a jar of clear water. See? It begins to split up. Parts of the drop sink and swirl in different directions. At last, the colored drop breaks into so many parts that it has become part of the whole jar of water. The molecules in a liquid are moving all the time, pushing and pulling each other, attaching to and breaking away from neighboring molecules. The molecules in the blue drop break apart because they are pushed and pulled all over the jar by the other water molecules. The energy that keeps the molecules moving is heat. This heat can come from the sun or the room in which the jar is standing. Without heat, water would not remain a liquid. Ice. When water cools, it loses energy. The molecules slow down and eventually stop swirling and pushing each other. When water freezes, the molecules lock together, forming a rigid structure. A drop of blue water no longer moves. The water has changed from a liquid to a solid, ice. Ice is a solid like metal or rock, but unlike metal or rock, ice is solid only at temperatures of 32 degrees Fahrenheit, 0 degrees Celsius, or colder. At room temperature, ice melts, changing back to a liquid. See how it's melted? I wonder if that's the blue drop of water from here. I wonder if they froze that. Ooh, water vapor. Water also always seems to be disappearing from wet clothes on a line, from puddles on the ground, and from dishes on a draining board. We say it has dried up, but where has the water gone? Just as water can be a liquid or a solid, it can also be a gas. The water from the wet dishes evaporates. That is, it turns into a gas called water vapor. Molecule by molecule, the water from the drops on the wet dishes drifts invisibly into the air. So look at the changes here from the forks. Heating water in a kettle speeds evaporation. Heat from the stove makes the water turn to steam, which is extremely hot water vapor. When the steam hits the cooler air, tiny droplets form, and we see a cloud just beyond the kettle's spout. Almost immediately, the drops evaporate and change back to invisible vapor. Then the water molecules mingle with other molecules that make up air. All right, condensation. The air around us always contains some water vapor. Water molecules move rapidly through the air and hit everything in their paths. The molecules bounce off most warm surfaces, but stick to surfaces that are cold. In these photographs, molecules of water vapor stick to the coldest part of the glass. Gradually, droplets form on the glass as the molecules accumulate. That means there's more of them. Water vapor changes from a gas to a liquid. That is, it condenses. So you can see it here. So you can see on the outside, and then look at how it goes there. You can see it on the outside of the glass. I know that happens a lot of times at a restaurant because they put a lot of ice in your drink, and you can see that. Let's look at evaporation versus condensation. In the photographs above, so these, why do the water drops outside the glass disappear while the water drops inside remain? Outside the glass, the water evaporates and spreads throughout the room as vapor. In time, the drops disappear. Inside the glass, water also evaporates, but I can't talk. But the vapor is trapped. The air inside the glass becomes humid, which means that the air is full of water vapor. And that vapor condenses back into the water drops as quickly as water molecules can evaporate. Therefore, the drops remain. So if you live in Ohio, you know about humidity because we get a lot of humidity in our air. We have a lot of that water in our air, especially in the spring and in the summer. You can feel it. And if you travel somewhere out west where there's a desert, you can feel that difference when you go out there because your body doesn't sweat as much. Maybe your hair might react differently. But that humidity, you can feel it in Ohio. So you guys are probably familiar with that. All right, remove the glass and the vapor expands throughout the room. So evaporation continues, but condensation slows down. In time, the uncovered drops will disappear. Ooh, there's that pin again. It says how clouds form. Clouds are made of tiny water droplets, too small to be seen without a microscope. If a cloud droplet is to form, water vapor must first condense on a particle of dust. Carried by wind, these dust particles are often bits of pollen, soot, soil, or salt. This experiment shows how cloud droplets form. Salt is placed on a jar lid above a dish of water. Okay, so you see that there's like a little dish of water, and then there's like a jar lid, and there's salt on there. A glass cover traps the water vapor, so you can see the glass cover. In minutes, the vapor condenses on the salt and coats each grain with water. Hours later, the salt dissolves in the water drops. So look, here's the salt. So they had that shut in there. So this is just a zoomed in version of that. Now look at the salt. Now look at that. Clouds form when water evaporates from the Earth's surface and rises into colder air. There, the vapor condenses on cold, airborne particles. More and more molecules cling to the particles until droplets form. It takes about 1 million cloud droplets to make one raindrop. Rain does not taste salty or appear gritty because the particles that allow clouds to form are usually too small to be noticed in raindrops. So that's another cool little experiment that looks very easy to do. And I think they have the pin in there just for us to understand the size. You could just do that with, a little glass of water, a lid, and then some sort of cover with that salt. You could totally do that easily and see if you get the same results. Ooh, snowflakes. This is why I really wanted to read this book because we've had our first snow and it's so cool to see these images of the snowflakes. So it says this snowflake is shown 60 times its actual size. So that means they took its size and they made it 60 times bigger. The angles between the 6 major branches, so here's our 6 major branches, are repeated over and over in many of the smaller details of this amazing structure. How can such an intricate object form in the sky? Cloud droplets form when water vapor condenses on particles. But in very cold air, water molecules that cling to particles form tiny ice crystals. As more water molecules from the air freeze onto the crystal, they join at angles that allow a 6-sided structure to form. If the crystal grows large enough, it will fall to the ground as a snowflake. Clouds that produce snow often contain both ice crystals and liquid droplets. At the center of the snowflake is a cloud droplet that froze, allowing the snowflake to form around it. Scattered throughout are other cloud droplets that have frozen onto the snowflake as it fell through the cloud. Sometimes snow mixes with pellets of sleet, which are frozen raindrops like the one shown below. See here? By contrast, snowflakes are ice crystals that form when water vapor changes directly from a gas to a solid. So this is actually sleet 15 times the actual size. That means it's way smaller than what we see there. All right, let's look at some more snowflakes. So it says endless variety. Many ice crystals grow into shapes that are just tiny slivers, rods, or clumps of ice. Of these, the underlying six-sided structure may not always be visible. But when weather conditions are just right, the crystals will grow into an astonishing variety of elaborate six-sided designs. All of the snowflakes on these 2 pages were photographed on the same day. All share the same angles, but vary in design. One has 6 branches of unequal length, giving the appearance of a 3-sided snowflake. Where's the 3-sided snowflake? It looks like one, but it's not. This one. Another snowflake has only 4 branches. Look at that one. Apparently, 2 of its branches didn't grow. Well, odd variations like these are typical because different conditions of humidity, wind, and temperature affected the growth of each snowflake as it fell. Each design holds secrets of its unique journey to Earth. When a snowflake melts, its intricate design is lost forever in a drop of water. But a snowflake can vanish in another way. It can change directly from ice to vapor. The sequence below shows a single snowflake as it gradually disappears. So you can see how it gradually is disappearing as it's melting. By the way, these snowflakes here, these 12, this is the actual size of them. So you can see they've blown it up, and they have a really awesome camera that they're using to be able to see all of those details in the snowflakes. They're absolutely gorgeous. I like them. I also like this. Look at the frost and dew. On some days when the air is humid, a sudden drop in temperature during the night will cause water vapor to condense on cold surfaces. By morning, the landscape is covered in sparkling drops of water, dew. If temperatures fall below freezing, the cold weather relative of dew appears, frost. On windows, frost forms along tiny scratches and other imperfections in the glass. As with snowflakes, frost is the result of water vapor changing from a gas to a solid. That's why the angular structure of ice crystals is evident in the fern-like patterns of frost. See how it looks like a fern, like the little plant? When dew forms, so this is dew on a spider web. When dew forms, a short walk through the grass will soak your feet. On spider webs, dewdrops appear like glistening pearls. In this photograph, we can see how water reflects and bends light. An upside-down landscape appears in each drop of water. Ooh, that's something we're going to talk about with light energy this year. I believe that's on this next page. Yes, water and light. So if you look carefully at this beam of light, you'll see the mysterious way in which light interacts with water. Some of the light is reflected, which means that it bounces off the surface of the water. But some of the light passes into the water. As the light enters the water, molecules bend the light or refract it. The bent rays of white light are transformed into all the colors of the rainbow. How is this possible? White light is made up of waves of many different sizes or wavelengths. The shortest wavelength, which we see as violet, bends the most. Red is the longest wavelength, and it bends the least. All the other colors fall in between. So you might know that Roy G. Biv, that red, orange, yellow, green, blue, indigo, violet. Those are actually wavelengths that we are seeing. And they bend at different, they bend in different ways depending on the length of the wavelength. So that's going to be something we're talking about in light energy. Sun shining on spray from a garden hose creates a rainbow. The spray produces drops of water that bend the light and flash bright colors when seen from the correct angle. Natural rainbows work exactly the same way. The sun must be behind you and low in the sky. The arc of the rainbow is caused by the sun shining on billions of spherical raindrops that fill the sky. Ooh, the water cycle. The sun's heat and the Earth's gravity keep water in constant motion. Water evaporates from puddles, ponds, lakes, and oceans, from plants and trees, and even from your skin. Water vapor moves invisibly through the air, but it is also ready to condense on a cold blade of grass or the surface of a pond. Massive clouds form as vapor condenses on tiny particles of dust in the air. Then, and only then, can water fall from the sky as rain, replenishing lakes, rivers, and oceans. Hard to predict, impossible to control, water cycles around the earth. And water is precious. Without it, not a single living thing could survive. No plant would grow, not even one blade of grass. No animal would roam the earth, not even a spider. But somewhere in the world right now, snow drifts on a mountaintop and rain falls in a valley. And all around us, we are reminded of the never-ending journey of a drop of water. There is some information at the end here with some different observations and experiments. I hope you learned something new about water that's all around you. That's all for me. Take care. Peace.